All right. Hi, everyone. Welcome to the CAIS seminar. This might be one of the last in our series this semester. Today's speaker is Shubham Singh, who's a PhD candidate in computer science at the University of Illinois, Chicago. His research focuses on computational methods for tackling socio-technical challenges. Um, he works on resource allocation, fair machine learning, privacy, and security. He has published at a lot of venues, including AMO, Usenix, and ICML in Europe. And he has been recognized by various awards on mentorship as well as service. So today, Shubham will be talking about his work on fair scheduling and resource allocation for public services. So take it away, Shubham.
Yeah. Hi, thank you so much for the introduction, Professor Sabha. My name is Shubham Singh, and thanks all for coming this afternoon to this talk. And I'm honored to be here and for this giving this seminar on fair scheduling and resource allocation for public services. So before we jump on to the main content of the talk, a little bit about me. So as Professor Sabha said, I'm a CS PhD candidate at University of Illinois, Chicago. I work closely with Professor Chris Kanish and Ian Cash, and I work on socio-technical challenges and I'm trying to address them by developing computational methods. Besides my co-advisors who are Kanish and Cash, I have collaborations with research communities in EMO Bridges, which is formerly known as MD4ST. I also have collaborations with researchers at MPI Software Systems and industrial researchers at Hugging Face. So I see my research broadly in three verticals, and the first one is fair machine learning. And in that vertical, I employ techniques for empirical analysis to develop methods that make machine learning output more fair. In the second vertical, which is what I call the computational social science, I deploy techniques for mathematical modeling and theoretical analysis to abstract away certain problems that are faced by public sector problems, and then model them and try to come up with measures that can improve the delivery and efficiency of those public sector services. And the third vertical is also privacy and security, where I deploy methods like user studies and qualitative analysis to extract people's values of their data and accounts used in online platform services. Today we'll talk about the first two verticals, and for more of the third vertical I can talk later. So I divide this talk into three broad research questions. The first one being, how can we use predictive algorithms to improve efficiency and fairness of public service delivery? The second one being, when the resources change, how does this change in resources can affect fairness and efficiency trade-offs in allocation settings? And third, what kind of trade-offs are offered between efficiency and fairness with scoring-based ranking systems when you're trying to rank a couple of documents or a couple of applicants or a couple of things to do in an ordered fashion. So and I focus mainly on public services because of various reasons, and some of the examples include like child protection, rehousing program, and food safety. These services are usually undertaken by local or state governments and provide for free for no cost to its citizens. And they basically provide a safety net to the marginalized communities. They foster inclusive society, and for people who don't have all the resources endowed to them, they also help balance the scales a little bit. So it helps in their well-being and fosters the community. There's some challenges that come with delivering these public services. The first is human decision makers. So usually when people have to apply to get these services, and there's a human decision maker that determines if an applicant is applicable to receive the services or not. There's some bias baked into it. The response time for delivering these public services is critical. So people who need help right now, the more delay they get in the receiving the services, the more worse they'll off be, and we can't do them as much benefit as if we're done sooner. And then finally, since these services are provided by local governments, they're strapped for resources, and these agencies usually work under resource constraints. So given that these challenges of like public decision makers critical response times and limited resources, people have applied or tried to apply AI and predictive algorithms to deliver these public services. So the first work we'll look on is called Fair Scheduling for Food Inspection. This work was published at EMO 2022. And before we jump into the meat of this work, it's important we look at the background. So the background is this report that came out from the people at City of Chicago, which involved data scientists and a bunch of people from the Allstate Insurance. And this report basically claims that they can forecast restaurants for critical violations in Chicago. So what's a critical violation? So unlike here in California and Chicago, restaurants don't get A, B, C, D letter grades. They get pass or fail. And this pass or fail is determined based on the number or if a restaurant can get a critical violation, where a critical violation is the highest order of violation and has the highest likelihood of resulting in foodborne illnesses. So if the restaurant is serving bad food, which is unsafe for consumption or doesn't match up preset criteria given by a food safety code, then an inspector can cite a restaurant as a critical violation. So if you get it, you'll fail the inspections, and you can't serve food until you fix the violation. So the detail of this prior work, which we'll call Sheng Junior et al. Throughout this talk, was looking at routine restaurant inspections. So a restaurant can be inspected as a response to complaint, but we'll focus on the routine inspections today. And what they did was they basically, when I say they, the researchers, they basically used the historical data to train a linear model to find restaurants that have the highest likelihood of finding critical violations, because their objective was to find these restaurants quicker so that they can catch them and people don't get exposed to all these foodborne illnesses. And what they found that on average, if they use this schedule gotten from the predictive model, they were doing 7 days better on average. So basically, they could find critical violations on restaurants 7 days quicker than business as usual, which was the default or random schedule that sanitarians were following. So diving deep into the data set, it contained around 18,000 rows for routine inspections and spanning over 3.5 years of training period. And they had a special testing period where restaurant inspectors sanitarians were going and doing inspections business as usual. And they took this data set, stripped away all the final outcomes and fed it into the model. And that's when they found 7 days of speed up. And looking at the features, it contained a lot of restaurant-based inspections. So if the restaurant allowed consumption of tobacco or consumption of alcohol, it had details about location, so zip code, the coordinates of the location, the weather conditions on the day of the inspection. So how hot was it? What's the maximum temperature on the day the inspection was done? And the most critical one is sanitarians. So, and we'll see why it's critical. But because since this study was done in public domain, they didn't want to release the names of people or inspectors who were doing this. Yes. Sorry? So sanitary inspections are same. I'll use them interchangeably. So these are identifiers of people or inspectors who were going and visiting these restaurants. And so that was used as a feature in the data set. Yeah, good question though. So yeah, as I was saying, to protect their individual identity, they didn't want to release the names of these sanitarians because they planned to release the data set. So what they did was they basically clustered the sanitarians based on a critical violation rate and named them based on Chicago transit lines. So here, as you can see in the table, the first row says the sanitarian cluster name, which is named purple, blue, orange, green, yellow, and brown. And they're ordered in the rate of their descending critical violation rate, where a critical violation rate determines how often a sanitarian cluster is giving out critical violation, which is the highest level of violation, divided by the total number of inspections. Yes.
Sanitarians did not work across different trains or transit lines.
So transit lines are independent. There's just names given to them, but yes, to dig deep, they do have a certain jurisdiction or what you call beat. They frequent certain regions more often than the others. So there's some geographical element to it. There might be some overlap, but more we'll see in the next slides. We also plot them on the map and see what's the correlation. But as you can see here, there's a huge variation where purple and blue are the harshest sanitarian clusters with 41% and 26%, and the lowest are 6% and 3%. So they range from 41 to 3%. Depending on who inspects your restaurants, you can get a different varied output. So what we see here is that the model-driven inspection schedule can result in unequal health outcome, and we define this unfairness as time to find critical inspection differing across various city regions. And we'll see how this is driven by the variance in sanitary violation rate. To mitigate this, we try to use fairness-aware prediction models and see it only mitigates the cause of unfairness, but does not eliminate them. But just how you use the model scores in the broader pipeline of getting the inspections can change, can lead to fair outcomes, and it's also pretty dominant amongst all the approaches that we test. So we need to define what defines the schedule as fair or efficient. So basically, we define schedule efficiency as expected time to find a critical violation rate given by this y variable equals 1 in a given time period, and the lower value is better. So we want to find those restaurants quickly. And then group fairness is defined as the equal expected time to find a critical violation across all the groups. So if they're equal, the schedule is group fair. So using the location information in the data set, we use the zip code to map all the restaurants and inspections done to 9 major city regions. And we define fairness violation as this difference between average time taken to find a critical violation rate in a specific region minus the overall average. So how worse or better you're doing compared to the group average. So pictorially, I will use this plot a lot. So I want to go over this plot again. So on the x-axis, I plot those 9 city regions, as I mentioned, and on the y-axis, I show the violation, fairness violation. So if you are close to this horizontal line on 0, basically, your detection time is very close to the group average, so your things are fair. You're better off on average than the whole schedule if you're below this line. So if your number is negative, you're having a earlier detection of critical violation rate. And if you're above, that means like you're worse off than the group average. So when we plotted the default, the random schedule that the sanitarians were following before any predictive modeling was done, we can see things were slightly unfair, but like for most of the regions, things hover around this 0 line. But in contrast, when we plot the Sheng Jr. et al., which is the work done by the city, in the orange bars here, you can see like for north and far north, they're doing much better on average time to find critical violation rate on the cost of the time taken to the delay that is experienced by southwest, west, and northwest. So like their time to find critical violation goes way up. Yes. Like here on average so are the different numbers of residents? Yeah, good question. So I think as I mentioned in the metric that they report, it was based on a single snapshot. But what we did was to basically, so we were able to replicate that, but we also did like a moving so k-fold testing across all the, so basically we wanted to find out there's nothing special going on in this 2 months of testing. So basically we moved our testing window across the whole data set, and then you could see sometimes the average was more than 7 days as well. Good question though. So we want to dig deeper into like what's the cause of unfairness, and then as there's a question earlier, we did see a correlation between the sanitarians when they're doing inspections and city regions. And so on the left, I plot basically the purple cluster sanitarian inspections, which is the harshest to remind you with the table here at the bottom. And the brown is more scattered on the far northwest and southwest. And if I change the same plot we saw on the last slide, but now condition them based on sanitarian clusters, you can see this, the purple and blue sanitarian inspections are driven way higher or being scheduled way earlier than green, yellow, and brown. And these are again in the order of their descending critical violation rate. Very good question. Okay. So to mitigate this, we explored 2 classes of fairness approaches. So how can we make things back to fair while trying to also gain some efficiency benefits. So we at the time we looked at the best available three fairness evaluation models. The first one was Zafar et al., which had in the framework they allowed the sensitive attributes to be polyvalent, that is non-binaries, instead of having a 0, 1 sensitive attribute. In our case, it was sanitarians. So Zafar et al. Worked well for us. We also explored the Raza et al.'s work, which guarantees robust fairness guarantees against adversarial distribution. And we also explored Krishnaswamy et al.'s work, which basically works by learning a set of randomized classifier for each group, and on average gives you some lower bound guarantees on unfairness achieved. And the second is, as I said, we just modify how the prediction score is used in the scheduling process, and we'll show two approaches to do that as well. So in the same figure we saw earlier, if I plot the unfairness violation by Zafar et al., we can see again things are getting close to the fair bars in the blue here. In contrast, when I plot the same from Raza et al., one caveat for this implementation was that they only allow for binary sensitive attributes. So we had to binarize our sanitarian clusters from 0, like 1 and 0. So purple, blue, orange being high, being the preferred group, and green, yellow as the unpreferred group. So you can see that the bars are still higher up. And the blue bars here again represent Krishnaswamy et al., and you can see there's still some variation. So now we've just explored how these we are changing the output of the model to be fair, but how do we go from the model output to a schedule? So in random, as you can see, I take this stylized example. You can imagine the order is 1, 2, 3, 4, where 1 and 3 belong to purple sanitarians and 2 or 4 belong to the brown sanitarians. For the city or Sheng Jr. et al.'s work, they're basically boosting or prioritizing the work inspections done by the purple. So you can see 1 and 3 are scheduled up. But in our work, what we're trying to do is maintain the within cluster priority, but changing what you can schedule within those clusters. So if we take this approach and extend it to the full schedule, which the first version is what we call a sanitarian blind approach, where at the test time we basically take away all the information about sanitarians and use the model output. And in cluster sort is the approach where we use the models output as is, but only allow reordering within these clusters. And if I plot them here on the same graph, we have seen the green and the red bars depict the fairness violations from those two approaches. But what we're looking so far is only fairness violation. We don't know how well we are doing in terms of efficiency. For that, I plot a efficiency and fairness trade-off. So to read this graph, I'll say the x-axis depicts the fairness violation. So the lower the fairness violation, the more fair you are, and schedule efficiency goes down. So a schedule which is super fair and super efficient would be the bottom left corner of this figure somewhere here. So the first dot represented here, the default, the random schedule, which is called the default, is doing way better in terms of fairness violation, but also has a higher schedule efficiency. On the bottom right, when I plot the efficiency and fairness violation, you can see Sheng Jr. et al. Is the opposite end of bottom right, where it's like super unfair, but also gains so many days on average based on schedule efficiency. Very close to the default lies our in-cluster sort approach, where it gains a couple of days worth of efficiency by sacrificing only a little in terms of unfairness. And this trade-off is again seen by the sanitarian blind, where it gains a little bit more efficiency by giving up on fairness violations. And all other approaches which were based on training the model lie on the inside of this Pareto front, plotted by the dashed gray lines. So our approach, which is in cluster sort and sanitarian blind, do lie on the Pareto front. The takeaways from this work was that when applied naively, these predictive models learned the the variance in sanitarian violation rate, and the schedule taken out, or like output from this model, can result in an unfair schedule based on, and can affect people differently based on their location of work and home. And just by modifying how you use the predictive scores can lead to fair outcomes without the expensive need to retrain the model. And we demonstrate our findings based on the food inspections, but one can also apply this to other citywide services. Before I jump on to the next work, I can take some questions. Yes. Find out what are their skillful or Yeah, I think so. Based on our interaction, so we interacted with the city for a bit. We also talked to a bit of food scientists in this course of this project. I think people definitely would be unhappy in terms of like if you were to like just reassign their regular schedule of like where they're going because of travel times and all these things. So basically, if I were to like plot this, it could also take a traveling salesman problem of like what's the minimum disruption you can do. Yeah, yeah. So right, right. But then I think what we were and the finding that came out, the soft finding that came out from this work was also this variation in sanitarian violation rate is not only like just localized to Chicago. There's another paper which is done in Seattle, King County. They observed the same that humans in the decisions are very biased given on any random day and given on what restaurant they're inspecting. So we also saw like a use case because in this data set we didn't use it, but we had like descriptions of what made the sanitarians give out that outcome. And I remember one example where the inspector didn't understand the language of the kitchen manager of the restaurant people were speaking. It's just like okay, failed. So like this huge, even though they're like standardized tests to like basically have them some sort of like have their output be some standard, we still see these variations throughout the.
Results some more.
Yeah, I think it's a good insight, but I think it would be interesting to explore. But again, like this reminds me of the things that probably like didn't were not interesting sign like from the paper perspective, but were interesting from us to for us to learn was that in some cases, so it also happens in building inspections. So like this correlation between the violation rate and geography is not just because of the variance in like human judgment. It's also because what do you choose to report. So in like poor neighborhoods, what these inspectors would do instead of citing the businesses with this violation because it has a adverse effect on the businesses, they would just ask them to correct them on the spot, right? Which is not recorded in the data set. So you could imagine like, okay, like I can do a much more random clustering of there. I have like equal distribution of like all these inspectors which have different violation rate, but I'm assuming that some of the confounding factors are not observing like this one, what I remember. Okay. Okay. So the next work we'll explore is efficiency, fairness, trace of state trade-off for allocation problems. So we looked at an empirical setting. Now we'll basically do some sort of mathematical modeling to see what kind of trade-offs behavior can we expect when resources change. So this was done to basically map the benefit received by giving resources to groups of people and using utilities to basically encapsulate certain behavior satisfaction they can get from imparting these utilities specifically to different groups. For that, we use utility functions as a common way to connect the benefit of resources to groups. And we define the utility as U sub G, where each group G receives some amount of resource of any given type and receives that benefit. So in a framework, you can have T different type of resources, but for the simplicity of this of these modeling, we look at one type right now. So what happens when the utility change as the resources change? So for that, we introduce this class of functions. Actually, it's a property of linear functions that you might have seen. They're called homogeneous functions. So homogeneous functions are the functions that follow this equation here, where we say if you take a function u of r, scale is input by a factor of s. If the output of that function is s to the power of k, where k is a homogeneous degree, times the original input, then we say this function follows homogeneity. And so a more pictorial representation of this. So like imagine we have a function with some quantity, is depicted by this purple square. If you scale it up, and we can write its output as the scaled quantity times k times the original input, then we say that the function is homogeneous. And then this class of homogeneous function is commonly seen in a lot of type of like common utilities. So a common one is linear utility. You can also have quadratic utility, which is also a homogeneous function of degree 2. And in case you want to represent more adverse scenarios, let's say pollution effect for marginalized community from industry, you can also get inverse utilities with degree of -1. This is also common in economics where people use utilities where Cobb-Douglas production function is an example of homogeneous function. So is Leontief utilities. So given the utilities of the groups, we care about some sort of objective function. And in this case, like I explore one of the objectives is like linear function. So imagine we have two groups or two quantities. We care about their linear combination. So this says that if we have a group 1 with which is a homogeneous function, another group U2 which is also a homogeneous function, we can depict its output, or we can say that the output of their sum is equal to the scaling factor, which is the blue box here, times k, k being the degree of homogeneity, times the sum of their original sum. So objectives like social welfare, where we're interested in some of utilities across groups, across individuals, is one example of this linear objectives. What about comparative objectives? So we want to, yes.
Yeah, so my question is, can you give us a little more motivation for why you think that homogeneous functions are really a particularly interesting class of utility functions worth studying in this context?
Yes. I will get to it as we get to the end. So I'm going to set it up, but like this is kind of my answer right now is this is kind of a way of understanding these simpler things, but I think I'll also test this assumption later on. So we'll see this. Shall I take the questions in the chat now, or shall I do it later? Got it. Perfect. Okay. So comparative objectives, let's say, for example, you care about fairness or like how much you're doing better from one group versus the other. So in this case, a ratio is a comparative objective. And since, again, we assume that U1 and U2 are homogeneous functions and we can take out their scaling factor, they both get canceled out and we don't see any effect of any scale of input here. So fairness functions, for the example, which some of the examples include demographic parity ratio or shortfall. If we used in the real world, we'll see no effect of change in fairness as resources increase. So now we're coming to like setup, and then like we've defined homogeneous functions, we've seen the objectives. So now let's look at utilities. So first we look at need-based utilities. So need-based utilities are where where a group can get some sort of benefit from the resources, which is more linear. So here let's assume we have group G1 and G2, and group G1 can extract twice as much benefit from the resources given to it versus group G2, which gets only the linear utility from them. So given these two groups, let's say we care about efficient allocation. So if we're being super efficient, we want to maximize our utility and sum of utilities, we'll give everything to G1 given it has a higher need for these resources. And a fair allocation, in this case, since we know what the utility functions are, we can equate them and we can get what sort of allocation for both groups can give us the exact equal outcome, and then from that we can get the solution for the fair allocation. So one example of this could be, for example, policing. Like if you assume that you have a higher need and then every additional resources give you a better, like a linear output, like that, then that's one philosophy you're following in terms of allocation. So if that's your philosophy, and then you want to define efficiency as the sum of, or the average of group over average group utilities, and fairness is some sort of distance, or L2 distance in this case, between efficiency and the overall group utility, and we use a big constant C to subtract that so that unfairness becomes fairness. So basically, this gives us some sort of a measure of absolute fairness. If we plot in the stylized example on the x-axis absolute fairness and the y-axis efficiency being the average of group utilities and absolute fairness being the difference between the group average and the groups, as our resources increase from these faded dots to like more solid dots, you can see the efficient allocation becomes more and more unfair in terms of absolute fairness. And the fair allocation, since we're solving a posterior, it stays fair, but as you can see, it gets slowly and slowly more efficient, but not as the same rate as the most efficient allocation. Let's keep our allocations the same, but let's just change how we are measuring the fairness. So on the x-axis, instead of doing absolute fairness, we're doing a ratio of the group with the lowest utility to the one with the highest utility, and this is extendable to like more than one groups. But if we keep everything the same and just change the x-axis, we can see the efficient allocation again is super unfair because we're not giving anything to group 2, and the fair allocation is super fair, and there's no change in the fairness of either of them. So this is a degenerate case, but we'll see how this becomes when this becomes interesting later. So things become interesting when we look at outcome-based utilities. So for example, like in Chicago, there snow falls and we want to like plow, we have to have snow plowers come and plow the streets, right? So in this case, the number of the streets are fixed. So every additional resource that you add will give you a marginal benefit. So an abstraction of that would be something which I show here in the slides, where and every additional resource will give you 1 minus 1 over x utility. And again, if you assume that two groups get different utilities from these outcome-based utilities, and you calculate relative fairness as we showed in the last slides, again, I show the same plots, but if you solve for efficient and fair allocation, you can see on the left-hand side, based on now outcome-based utilities, the efficient allocation, which was becoming more and more unfair, now is edging more and more towards the absolute fairness as you increase resources. So the saying rising tide lifts all boats like matches here in the sense that given infinite resources, even if you're trying to be super efficient, you'll get close and close to unfairness. And if you change how you're measuring relative fairness, the same solution, but just change how you plot their relative fairness, you can see you can achieve a better relative fairness for the same amount of resources as when you were measuring absolute fairness. And finally, we looked at some things to optimize. On the y-axis, we're always like maximizing the efficiency, but what about things to minimize? So in this case, cost. So again, if we change the utility from being something to maximize to something to minimize for, in this case, 1 over r and 1 over 2r, but we plot the same figures. The left subfigure is less interesting because it's like a mirror image of along x-axis. But on the right subfigure, as you see, the cost goes down as you increase resources, and you start at like not 0. So the efficient allocation is still, it gives you some sort of relative fairness, but again, we don't see any change in the efficiency of in the fairness of the efficient allocation, and any additional resources basically don't show the benefit in fairness. So if you were to do this basically you can come out with an incorrect conclusion saying that any resources you're pouring into the allocation mechanism, you don't see any benefit given this combination of cost and relative fairness. So going back to the question that you asked earlier, this was all done in a static example where we can assume and basically come up with functions that kind of depict some sort of like utility functions, but what happens in real life? So if you use the Chicago inspection data set I talked about in the first set of work, but here we don't know what exactly the utilities are, so we can't solve for fair allocation. There's so much we can do better in terms of fair based on what we know a priori. But we change how the resources, the number of sanitarians who are doing inspection changes. So as you can see, and we plot the edges, and we plot the ends of the Pareto front where the dot represents the most efficient and the triangle represents more fair. The trade-off kind of converges as you increase more and more resources and calculating efficiency and absolute fairness. And this trade-off converges sooner if you're changing x-axis to use relative fairness. But here on the right subfigure, as you can see, as we saw in the static example, as and when we're pouring more and more resources, we don't see any effect of increasing resources for the relative fairness of efficient as well as most fair outcome that we can achieve. So in this case, if I were to randomly choose these two combinations, I would come up with the outcome that adding more sanitarians to our system is not giving us the benefit that we should. The takeaways from this work is that homogeneity kind of can give us a framework to guide what to expect, what can happen when the resources can change given certain assumptions. The measurement of how you choose to define objectives can result in dramatically different conclusions. And all the findings that I showed here are independent of how you're doing the allocation. So it could be like a MLP, or it could be a machine learning based allocation, but we are working on the final utility, so they are independent of what we're seeing. Before we jump on, I can take some questions. How are we doing on time? Okay, I think it's okay. Yeah. Yes.
So can you motivate why you define absolute and relative fairness in these particular ways? How do they compare to each other? Why efficiency was part of this? I think I missed all the motivation of this.
Yeah, that's a good question. Sorry. I think so. In the fairness literature, the two common definitions of fairness are again given by this. So like you want to find how is one group doing compared to others. So in the two ways that are do, like demographic parity, statistical parity, whatever parity functions you want to define, they are some sort of like linear combination of group one or group two, or some summation of group one or group two, or any combination of groups. So that's one motivation. The other motivation, the other form of relative fairness that I use, again, as I probably mentioned in the slides, is again taken from the ratio version, where people want to compute demographic parity ratio. So it's the advantage of using this sort of fairness definition is that you can say we are doing this much better compared to some baseline. So they're more interpretive compared to the difference, but we saw the pitfalls in which slide? So if say what? Why do I have efficiency here? So efficiency is just like giving you a lower bound. So like just like in the previous work, you want to see how much better you're doing, either to compare to the worst group or the overall efficiency. So basically efficiency, even if I remove this, you can do this for two groups as well. But we have efficiency here since we care about how far is the best group versus either the minimum group or the overall average. So basically, it's giving you like bounds of how far you're from the overall group average, basically.
Okay, and some follow-ups. Is there any way to choose one of the two notions in some cases? Can you somehow maximize both of them? Are they incomparable? How can I think about these two different?
Yeah, I think it would be interesting to look at both in conjunction, but from what I've seen, based on my read of papers and in general how people do this analysis, that since efficiency and fairness have a trade-off itself, they choose one and choose to go with one or the other. So another example that comes to my mind is price of fairness. So like price of anarchy, price of fairness is a commonly used notion in literature, and then if you track that back, yeah. Yeah, I think that's something interesting that I haven't done, but it would be interesting to see what sort of notions there are.
While we're on the slide, what does the notation in the exponent mean?
Oh, this is basically just taking
Just the exponent.
This one?
That one, yes.
Yeah, this is like a geometric mean of all the groups. So you're doing a product and then you're doing a 1 over. So like if there are two, it'll do a times.
I mean, what does curly brace G?
This is the size of the number of,
right? Or do you
yeah,
mean the union of the two groups? Or
no,
just
no,
that
size.
the number
No,
two.
two.
You're
Yeah.
just writing the number 2 in a complicated way.
Yeah. Sorry. Yeah, I should simplify this, but like the way we're implementing it was for more than one group, so I think I just chose the two ones. But yeah.
Vistra's question is absolute fairness more robust of a metric than relative fairness?
So I think that choice of robustness is kind of depends on the use case, which I said they both have the advantages. Like if you care about how if you know like what domain and what's the ranges they're looking for, then I think in that case absolute fairness is robust. But the advantages that's offered by relatives sometimes can also be appealing. But yes, like in this case, if you pair absolute fairness either with cost or like efficiency, that would be robust. But I guess that's also in the is a nuance of the use case.
Okay. We have like less than 20 minutes, so I don't know how much more you have, but there are two other questions which are related to the first part of your talk. We could come back to that later.
I'll quickly go over the next section, and then we can go on. So third section, I can quickly give you a brief motivation, and then we can probably take questions. Yeah, okay. So we also look at as I said, the trade-offs offered by scoring-based ranking mechanisms. So ranking is commonly seen in a lot of use cases. So ranking is when we present a set of documents, certain items in a linear fashion, and then the degrading element to choosing one over the other. So in this case, if you are choosing to inspect one restaurant first, you're choosing to inspect the next restaurant second, and then let's say in case of hiring, we have only 2 spots, then the first 2 spots will get the job and second does not. So usually in ranking, we have, let's assume there's like D documents with X features, and we also assume each document belongs to one group. So given a query, we want to learn a function f of x that produces some score that can be used to rank these documents. And this f sometimes can be given by the experts, could be learned through the features, and then is usually called by relevance. And it's called relevance and is the basic setting for learning to rank systems. And once we have the scores, we can basically sort the documents, which maximizes the user utility. The nuance comes in when we include another objective of minimizing unfairness. So in fair ranking, again, we have, let's say, a set of documents. We want to maximize utility. And in this example that I borrowed from Singh and Watkins et al., you can see like that individuals A1 to A6 have their relevances next to their icons. So like 0.8, 0.81, 0.80 to 0.79, 78, 77. If you order them based on their relevancy score for the task of hiring, you can see the absolute difference between their relevance is slow, but since you're making decisions one after the other sequentially, the chances of exposure that they get decays much more exponentially. And let's say if there are only 3 positions that have to be fulfilled, they'll all be taken by the candidates belonging to this one group, and the others will not get anything. So in our approach, we look at ranking from by the perspective of optimizing the utility, which is the average exposure gained by the positions at each position, and the unfairness, which is the average exposure for group A minus the average exposure from group B and their absolute difference. So since and we find that utility is some decomposable, whereas unfairness, as we define it, is not decomposable. So if you take the existing learning scoring to rank functions, even if they are like optimizing for fairness, they fail to achieve the optimal trade-off between efficiency and fairness, whereas an approximate ex post ranking, which kind of learns relevances and then tries to pick one group document over the other, can achieve better in terms of the absolute trade-off between efficiency and fairness. So we can go over definitions. Instead of doing that, I'll just go over the major results. So our utilities and unfairness are similar versions of unfairness we have seen. But what we show is that any group of any pair of utility and unfairness functions are not strongly scoreable. Strongly scoreable meaning they don't achieve the maximum trade-off between efficiency and fairness given as alpha times utility minus 1 minus unfairness. And given that we're scoring and ranking them based on deterministic factor. And similarly, let's say if it relaxes definition of strong scoreability and allow a distribution to be gained from distribution over this set of documents, we can also show counterexamples where the utility and unfairness gained from scoreability, from scoring functions, do not achieve the best optimal trade-off. We propose some alternative scoring, which kind of greedily take we really pick one document from either of the group based on the relative fairness, and also expand to beam search, which is common in NLP techniques. But the point of this work is not to propose a new post-processing method, but any post-processing method kind of looks at more than just the document itself, will do better than any scoring-based methods. We show experiments on synthetic data set and German credited data set. Here, the orange line represents our beam proposed approach, and the green one represents greedy, and the PL relaxes the Plackett-Luce ranking version, which is a version of randomized ranking. And as you can see, for all the alpha values shown from 0 to 1, favoring absolute utility to absolute fairness, we are doing better in terms of the trade-off. So the takeoffs were, we look at this ranking problem and challenge a common paradigm used in the ranking. We show that scoring is limited because the fairness definition is not decomposable, so you cannot any method that looks at the document scoring them one per document will fail to achieve the absolute best trade-off, and an approximate exposed solution are tractable and can do much better in terms of trade-off. I can go over future work. I'm looking at allocation plus outreach, how to combine resource allocation with outreach, try to come up with a framework for its distribution, which kind of does end-to-end of allocation and outreach, and partner with grassroots organization for validation. And this has applications for homeless assistance services. And I'm also looking at developing or looking into more preliminary work on multivariate scoring functions that might offer a better trade-off, which learn scoring not just per document, but on the whole set of documents and queries. Okay, thank you for your time, and I can take all the questions now.
Any questions? Okay, so we can go back to part 1 of your talk, where there are a couple of questions. Caroline asks, does an inspector inspect more than one location in a single day? If so, are distances between locations in a schedule taken into account when creating them?
Yeah, so from what I remember, they do inspect, and we do plot all the inspections uniquely. So there's definitely more than one inspections. There's no measurement of the distance and time to travel between those two locations. That's something we don't see in the data set. But I'm assuming with a different problem setting where we are measuring that could be taken into account, but not in the setting.
Got it. Another question from Bistra. How does the in-cluster sort and sanitarian ideas generalize to other applications? How can one summarize the general methodology being proposed?
Yeah, so I think that's a good question. I think the in-cluster sort was one of the approaches that kind of stemmed and basically pushed our minds to work on the ranking problem, because basically you're trying to come up with some sort of like prioritization of inspections and how to do them, and there's some sort of like structure preservation that if you follow that and like only optimize within the structure, then you can get some better trade-off without trading off a lot of unfairness. So like, yes, that's generalizable, and our scoring work kind of does that. What's the second half of the question?
How can one summarize the general methodology being proposed?
Yeah, so I think for this instance, I would say like this also has the added benefit of like respecting the operational constraints. So I think the question that Caroline had of like what are the distances and what happens if we perturb the distances too much, assuming the things were happening there with some sort of like equilibrium. If we do stick, let's say, I'm assuming the sentience within clusters are fungible or interchangeable, right? If that's true, then I would say like within doing this within the structure of how inspections were done, and using that information can give you some sort of technique to like do things more fair and also efficiently. So I think that's my broader generalization, but I would also go to the ranking work to say like this is the reason that it can do things better in terms of generalization.
Other questions? So I have one question, which is kind of a naive question about this project. It's like you found that the schedule was this confounder that kind of had these fairness implications, and
Hmm.
is that a fair
I
assessment?
guess like
Yeah.
what do you mean by
So if you
confounder?
go back to the initial slides where you were showing the results, did Schenk et al. Take into account some kind of
This one?
yeah. Here, do they take into account some kind of scheduling?
No, clearly not. Because if they
Okay.
did,
Yeah.
the whole thing would not have been a thing, which is what like caught us by surprise as well. Because
Right.
the 7-day improvement that they claimed was solely based on the 2-month period simulation that they did.
Right.
And I think based on conversations with them, as long as they lasted, was that they did try it but did not end up adopting it,
Yeah.
which would have come with other headaches that like operational feasibility and stuff like that.
Yeah.
But
So,
yeah,
okay, following up on that, my question was that um, are these factors that, let's say, you are able to find which affect fairness, are these only discoverable post hoc? Or are these factors that could be taken into consideration? Let's say Schenk, if they took into account the scheduling thing,
yeah,
uh, is that even possible when you're starting a study of this kind?
I think so. Like I think defining the goals and what the parameters are that you're willing to trade definitely kind of narrows the problem. And I think that would have been done maybe like, which is why I say like I don't know why they didn't take into account what the model is inputting and how that go into real world, right? Just the model output does not give you the full picture. So I think if there was one more cycle of development through and through, I think that would have been cut. So I think
Yeah.
it's
But there are possibly other factors that we don't know about which
sure.
could be affecting the outcome.
Yeah, I think yeah, because I think yeah, for us we observe what we could observe based on the data that they're willing to share with us, and whatever knowledge they're willing to like divulge to us. So yeah,
Yeah. So is there work that like kind of discovers these factors
like
like
auditing and stuff like that.
Yeah, yeah.
I'm sure there would be, but I wouldn't. I would say like the auditing in this case would just look at because they define their contribution as only the predictive model, but things go beyond the predictive model, and like you can correct for that beyond that. So I think if you encapsulate the whole problem, which probably includes the time to like visit different restaurants as well, maybe you can catch them, but I'm not familiar with the auditing framework that I'm familiar with. Kind of looks at the black box model and just looks at the output in a specific setting. But like this is another use case of like trying to predict one thing, but using it for scheduling because the model does not see that what's the downstream task that you're doing after the model's prediction, right? So
Okay. Other questions? Yes.
Do you know what the default schedule is based on? Like what factors is taken into account?
I'm that's a good question. I think based on my conversation and like what I got was this was so every set of cluster had or like cluster has like a team manager. So imagine like any organization you have a team manager instead of like sanitarians. So they found like okay, this is what is one routine and they allocated randomly. So, okay, like today you go to this restaurant, the other person goes to that restaurant, and that's what I imagine. So like a cluster, I imagine like it's like a team of sanitarians that are doing this work together. That's what I that's what my educated guess would be, but not I don't have the absolute truth for that. Yeah.
So it's close to like random allocation.
Yeah, definitely.
All right. I think so does anyone on Zoom have additional questions? So that might be it. So let's thank the speaker again. And I believe Shubham is around in LA for a while. So
Yeah, for as
uh,
long. I mean,
yeah,
going anywhere.
if people have additional questions or want to chat, you can get in touch.
That'd be great. Yeah.
Yeah.
Thank you so much.
Thank you.
Thanks for your questions.